a thermoset versus a thermoplastic material-based system. If you have that kind of a broader understanding, after all, that's good enough for you. I'm not even remotely thinking that at the end of this, you're going to invent a new molecule. No, that's not at all the intent of the focus, okay? All right, with that, what I'm going to do is, there is a YouTube presentation by this is a two-part thing. My colleague made a few remarks and I made a few remarks, and this is about the resins, and then after that I will lead you towards how you dumb it down to try to bring some semblance of mathematical relationship of determining the moduli or the stiffness, both are roughly same, and then the strength part of it. So that's what the goal is. And now, if you have the YouTube presentation you want to start.
I have these two videos.
Yeah, that's the first one. And they say first you start the, so I will pause it if you have questions, okay? Please don't hesitate. Go ahead if you want to run it.
Voice.
Why is coming back after slides of some?
You want to
Yes.
run it?
Video, audio
is coming.
So to a certain extent, this is a bit, not all, a bit of a repetition, somewhat, not all of it. But at least it will give you an idea from a slightly different point of view.
video player. Audio system is not system. Audio. No, actually we need audio.
No, I can't log into Google Meet in the system and play.
For the video. Yeah. Can you open Google? Just 2 minutes, please.
Sure.
You can distribute.
Oh, thank you. Yeah.
is there any polymers?
Yeah, it started.
Yeah, let's start from the beginning. And structure. My name is
Last contact participants.
I am Dr. Sugita and certain aspects of this module along with. This is the second of a series of modules dealing with the fiber reinforced polymer composite.
Maybe this is apparently the second. You want to put the first one first.
This is
That's what it said.
The first half
This is first one or second one?
It said second.
or aging of degradation issues of polymer composites under harsh
Actually, the file name is part 1
and
and
incorporates
two are there.
the degradation rates
Right.
under different environmental conditions into the design methodologies. The second part deals with the module, the second part module deals with mechanics of materials approach to fine elastic properties of composite lamina, including the longitudinal, transverse, and shear moduli. Also, stress versus strain relationships of composite materials in a two-dimensional lamina are discussed. The durability part is explained by Dr. Gupta, Barry Chair Professor of Chemical Engineering at WVU. With that, I'm going to hand this over to Dr. Gupta. Thank you, Dr. Gupta.
And I will be talking about durability of glass fiber reinforced composites.
These lights.
GFRPs are used in infrastructure applications such as rebars and underground storage tanks for chemicals. Once such a structure is in service, it is not easy to inspect it, but we still need to know if it will lose any properties and ultimately fail with time. We want to know when it might fail. There can be some visible signs of deterioration of a composite, and you can see that on this slide. There can be blisters or there could be discoloration. And you can see blisters in the column, and you can see the degradation and discoloration on the wrap at the bottom of
That
the.
is shut one of the two.
Reduce the sound. Reduce the sound. Mute it. Reduce the sound. Yeah, mute it. Yeah.
So we are talking about the definition of a durability here. As you can see, we talked about it yesterday. Durability is the ability to resist cracking, oxidation, and few other things, the wear and tear. The message I want to provide you here is this. Again, you don't have to know all these issues as a designer. But what we are saying is you will see that varying environmental condition. So that is the definition of durability. Where the reductions are coming, we explained or trying to explain that. Some of that will be further explained now, today, right immediately. But that is the requirement in a design. In other words, when you're 20 years old, you have a certain amount of strength. When you're 80 years old, you have a different amount of strength. So, in the same manner, a material behaves essentially in the same manner. You see what I mean? So, how much is that reduction? We have computed that based on certain kinds of basic sciences. I expose you what these sciences are. I did not really teach you how to arrive at it in depth, but I just told you in a broad brush manner, hey, this is how it's going to happen, and this is what we are finding over a 60-year, 80-year, or 100-year lifespan. If you are going to have a building or a bridge structure for 100 years, we have one kind of a reduction factor under different conditions. I'll give you those factors later. But on the other hand, if I want to have a structure or whatever the system, you want to have that surviving, say, only 2 years or 5 years, like what? A temporary structure, like a temporary bridge, those we don't design them for 100 years. So for those, the knockdown factors are different. So we will show you all that, but that's the definition of durability, and that is essentially associated with the reductions in the thermomechanical properties.
That come from exposure and you're interested in this because they do the reduction in thermomechanical properties of time and can ultimately mechanical properties change during service. Early on, the properties can
One of them
change
should
because
be
of what we call physical aging. The paradigm that is there in the polymer's community is that processing conditions determine the structure and structure determines the properties. Since processing is done over a short time scale, the structure that results typically is not an equilibrium structure. And as time goes on, the structure tends towards the total sense, and depending on the temperature and time of processing, the material may not be fully pure. So with time, there can be chemical reactions and there can be physical changes. These become very evident when the temperature is maintained at 2 in particular, there can be frequent changes over time in plastic polymers, and this results in mechanical property changes. The structure tends towards equilibrium, and this is not a bad thing. It does not result in any deterioration in properties. It's not detrimental to performance. What is harmful is what we call chemical aging. Here, the properties change due to interaction with the environment. There can be again, by environment, you mean the combined effects of temperature, moisture, presence of oxygen, freeze-thaw cycles, and so on. The consequences of chemical aging are changes in properties of the matrix, changes in properties of the fiber, and changes in properties of the interface between the fibers and the matrix. And these result in oxidation, hydrolysis, and other effects that are listed on the next slide. One can examine the influence of parameters such as pH, that we're talking about water, salt, or just plain water. Including temperature, humidity, sustained load, freeze-thaw cycling, constant load, UV exposure, and combination of these. And the modes of deformation that we can examine properties of a composite include tension or compression, bending, and break. Surprisingly, moisture turns out to be a very harmful agent by itself. It causes physical changes, such as lowering of the glass transition temperature, and what that does is to plasticize the matrix, and you can have significant changes when you increase C chain lowering in the T chain with 1 or 2% the concentration of moisture in the polymer. This affects the temperature and positive. In addition to this physical change, moisture can hydrolyze ester bonds within the matrix, particularly if you are using a polyester or a vinyl ester as a matrix, and this weakens the matrix. And this is made worse by addition of stress or increase in temperature. The fibers can also be hurt by moisture ingress. You can have leaching of sodium or potassium oxide from the fibers. There are micro cracks, and ultimately the fiber gets soft. And then it obviously loses its ability to bear a load. In addition, the resin, if it dissolves in the water that has gone into the matrix, it can cause osmotic pressure gradients, and this results in delamination of the fiber of the matrix. So every component of the composite can be hurt just by the presence of moisture. Our objective in understanding the durability of composites is to see what are the mechanisms of degradation, so that we can ultimately decide what safety factors we need when we design a composite for a 100-year service life. Typically, we do not have the luxury of waiting 100 years to see what might happen to a composite which is out in the atmosphere, out in the open. So we use accelerated tests and use equations such as the Archimedes equation. So that we can come up with knockdown factors or safety factors. One wants reliable equations for time-dependent property changes as a function of temperature and humidity, for example. To validate these equations, there's a huge need for natural weathering data for both vinyl ester and polyurethanes, so that we can predict long-term behavior. It is found that vinyl ester has better strength tension than polyester, and it is found that the mode of deformation that is very useful to examine is interlaminar shear strength, because this depends on the properties of both the matrix and the reinforcement. It is found that alkaline environments present a very damaging atmosphere, but this can be countered by the use of antioxidants, UV stabilizers, and moisturizers. So we obtain component data in the lab, and we correlate that with field data using equations which have been proposed to represent the behavior.
What are the abbreviations? VE and PU?
Vinyl ester and polyurethane.
Is a manifestation
Vinyl ester and polyurethane.
uses definition
And
under sustainable
Polyester. Polyester. P means polyester.
less than
Polyurethane. I'll define it.
PE stands for polyester.
PE is polyester.
Yes.
There is strain that occurs, and this results in microcrack progression. Interconnection avoids, softening the resin, and ultimately failure, which is a very undesirable event. If a composite is exposed to sunlight, a component of that is UV light. This can affect the polymer and result in discoloration, yellowing, and discoloration. And if the effect goes deeper, you can have change fission and loss of properties. But once the free radicals are formed due to the absorption of UV light in the polymer, and these free radicals can react with oxygen if it is present, giving rise to peroxides. Peroxides cause change fission and a reduction in mechanical properties. To minimize this effect, one uses UV stabilizers, and the approach could either be physical or chemical. One can put in additives like carbon black or titanium dioxide, or what we put in UV absorbers, quenchers, and stabilizers, and there's a wide variety of these materials available, and some of these are listed on this. Another mode of deterioration is stress corrosion cracking. This affects amorphous polymers more than crystalline polymers, which means that the matrix in the FRP is likely to be hurt due to the occurrence of stress corrosion cracking. What one finds is that liquid, say moisture, diffuses into the polymer. It softens or plasticizes the matrix. It makes it soft, and therefore at places where there is stress concentration, you can have creases which then lead to cracks. And obviously this is accelerated by an increase in temperature.
You want to pause it?
Another form of
Just a pause. I do not know how many of you know a little bit about stress corrosion based cracking. I want to say a few words about that so you have a better appreciation of it. You know what a corrosion is. There are a variety of corrosions. One of the many is oxidation. Right. You know what cracking is. You think you know what cracking is, but there is a lot more to it. What cracking does, how it makes a material weaker, depends upon what the type of crack you have. If the crack tip is extraordinarily small in terms of curvature, or conversely infinite in terms of its radius, then the stress concentration is infinity. But that's only in theory. That will not happen in practice. Whereas if you drill a hole, then that too has a stress concentration effect. And that stress concentration is of the order of about 2, depends on the size of the hole, depends on variety of material properties, brittle materials or ductile material, all that jazz, right? But my message is that typically that stress concentration is about 2, 1.8 to 2.2, in that general range. Typically, you will find a stress concentration in composite in the range of about 2 to 3, because there is no such thing as a stress concentration of infinity. That is just for discussion purposes. This is where the Paris law comes into the picture. Again, you may not know all those things, but what I want to tell you, what you need to go away carrying a message from this is that there are 2 issues. We call it stress corrosion cracking. It has 2 parts. One is the corrosion part, the other is the stress concentration part. And when you as a designer, I catered the course more towards a designer, not for a scientist. So you as a designer, what all you need to know is that this stress corrosion crack type thing leads to a bump up of extra stress formation by a factor of 3. So what does it mean? What does that mean? It means the following. If I have you saw a dog bone coupon, and if I pull that dog bone coupon, say I get stress to failure as 100 units, whatever 50 KSI, 80 KSI, whatever that number is. So you typically get, say, 100 units. Suppose I have a hole in there, and then I do the tension test, then what would I get? I don't get 100 units to failure. It'll be more of the order of 50 units or 40 units to failure. So this 100 divided by 40 unit is what is known as the stress concentration. So that is what he is talking about.
So one more thing.
Sure. Sure. No, that's fine.
Dr. Rakesh was saying that they get the data naturally from the FRP, and they correlate this data, especially for the shear failure, because this is the main cause of failure of the FRP. And so where this data is available, it's a naturally data.
An excellent question. Okay. We conduct these accelerated aging tests in the lab. So what does that mean? We have a pristine sample, we test it, we get 100 units, right? Then I cook the sample at certain temperature or with certain pH value or with certain thermal fluctuations or whatever, I get different values. So that is from the lab. So the question asked is, this data by the lab-based data, the accelerated aging lab-based data by itself has no meaning unless I correlate it to natural aging aspect of it. Now, how do I know that the progression or regression of the material strength going to be from the accelerated aging? How do I know how to extrapolate that in relation to the naturally aged data? That's $1 million question. How? We must have, so this is going to be, I don't know whether I had shown the actual Arrhenius procedure in my thing or not, but this is a log, semi-log scale from the strength point of view, from the strength on the vertical and the aging, the number of hours or number of years on the horizontal scale. That is the aging scale. So what we do, we need to get some rate of degradation coming out from the naturally aged material. Without that I cannot. But what I can do, however, is if I get a 2-year, 3-year, 5-year data, which is what we did, and I establish the trend, then I make a correlation between from this 2, 3, 4, 5-year data, then I extrapolate it to 100-year data. So that is, I have to curve fit. You all talk about AI business. There is nothing magical about AI. It is a statistical package. So don't get carried away with what the heck this AI is all about. It's all a sound bite to excite you and get it attracted. But we do that every day in your life, you know. Common sense, you know, it's more sophisticated than common sense, I admit, with AI, you know, but more or less. Therefore, in this curve, I'm going to fit a certain portion of the curve from the natural aging and then extrapolate how long that would survive. I wrote a paper, got good reviews on this. So if I demarcated the procedure steps, A, B, C, D, E, F type step. So again, if you send me an email, I'll be happy to share that paper, which define. In other words, in short, you cannot extrapolate aging based on the accelerated lab testing without a portion of that is properly correlated with the natural aging. Therefore, the rate at which a material degrades or ages in Himalayas is different from Kanyakumari. So you have to do these kinds of things at different locations, under different conditions, and thus you arrive at the correlation factors. Thank you. Go.
Another mode of deterioration is stress corrosion cracking. This affects amorphous polymers more than crystalline polymers, which means that the matrix in a FRP is likely to be hurt due to the occurrence of stress corrosion cracking. What one finds is that liquid, say moisture, diffuses in the polymer. It softens or plasticizes the matrix. It makes it soft, and therefore at places where there is stress concentration, you can have creases which then lead to cracks. And obviously this is accelerated by an increase in temperature. Another form of deterioration is fatigue. This is fading under cyclic loads. One finds that the fatigue life of FRPs is higher than that of conventional construction materials. However, fatigue life prediction is more complex in FRPs than in say metals due to anisotropy of the structure and the heterogeneity of the structure. And the behavior is influenced by the kind of fibers, the orientation of architecture of the fibers, how well the composite is made, and the nature of the matrix. So there are multiple ways of predicting fatigue life, and this will be discussed next by Professor Gallagher. Thank you.
In terms of cyclic stresses, or stresses are what we call the fatigue, we define it as follows. When a structure is subjected to cyclic loading, it fades at lower magnitudes of load than its static load to failure. That load to failure under fatigue cycles in composites is higher than the fatigue stresses in metals under the same stress amplitude, which is attributed to better ductility of polymers that transfer forces from one fiber to the other when compared with metals. However, fatigue-like solution in composites is more complex due to their anisotropy than in metals, where fatigue-like prediction is somewhat empirical. Obviously, fatigue-like depends on fibers, matrix, and manufacturing types. Stress rises from kinks, etc. And these stress risers can lower the fatigue line. Dr. Dieter and I developed strain energy-based fatigue-like predictions for composites, and several technical papers are available in this area. I suggest that you please go over these when you get ready to design composite specimens under fatigue. The next slide deals with the strain energy-based fatigue-like prediction equation development. I'm not going to get into those equation development. However, what I want to point out to you is the diamond shape blue-colored value dots are dealing with the actual experimental values, whereas the dotted green line is the strain energy-based fatigue prediction curve, for which we have an equation, and the red line is based on the stress-related fatigue response of a composite member. Here you can see that the stress-based equations are about 4, 5, 10 times more conservative than the strain-based responses and the equations developed in relation to the practical test data that's made available. And the data that we're comparing here is based on about 500 data points on the testing in length and in retention. The next slide is dealing with design recommendations. Herein, understanding of durability of composite structural systems under varying environments is extremely important to reasonably predict service life and incorporate these degradation factors in design by reducing the reference strength identified here as R sub 0 for a given composite material. A few of the degradation factors are shown in this slide, especially for moisture and temperature degradations. However, degradation factors are shown in the draft LRP code for other environments such as pH, sustained loading, etc. I suggest that you refer to several technical papers on this topic that I co-authored with other researchers and also independently. So fantastic work has been carried out and published by many other researchers across the globe. I also suggest you to refer to Mill 17 handbook, which is in the public domain. Broadly speaking, there are two degradation types to be considered in a design under fatigue. One is strength-based fatigue degradation factors. The second is the stiffness-based fatigue degradation factors. Obviously, the strength degradation factors are more severe than the stiffness factors in all loading scenarios except shear. That needs to be highlighted. In conclusion on the durability issue, I must say that understanding the durability response in terms of degradation mechanism is critical for safe and economical field implementation. These degradation factors have already been touched upon by Dr. Gupta a few minutes earlier. Moisture attacks, including pH variation, weaken the FRP composite strength more so than the stiffness aspect of the composite, because the stiffness is a function primarily of the fibers than the resin. Extreme acid environments tend to be more aggressive than extreme alkaline conditions. That is because the resin gets more affected than the fiber under acidic conditions. Alkaline conditions, however, are more detrimental to glass fiber composite than the tap water or solid water. Sustained stress tends to accelerate degradation rates and their properties under combined load and environmental conditions, as we have seen. Even though the test data is limited, we have some data to make that observation. UV radiation degrades the matrix dominated properties more than fiber-dominated properties, implying shear gets damaged more quicker due to UV radiation than tensile or blending set. Stiffness and strength reduction factors must be used in design considerations of FRP structures by reducing the reference strength that is defined as R star of 0. The next slide deals with the characteristics of composite lamina. Here, I'm going to briefly touch base upon the kind of mechanics-based models to predict the strength of a lamina that has so much percent of volume of fiber, so much percent of volume of resin, perhaps a little bit of voids. You can see in this picture.
Before I go too far into this component of my lecture, what I want to understand is, what is a lamina? What is a laminate? What is a component? And finally, what is a system? So, lamina is essentially, that's how we're going to build our theory, but what you need to know is that lamina is essentially one layer of a composite, whether it is a glass-based composite or it is carbon-based composite, it's only one layer. The thing that I passed around yesterday, if you recall, and if I just take one fabric, let's say that is 24 ounce per square yard fabric, then what do you get? And you soak it in resin bath, cure it, then what you get is a lamina. But that's not going to do us any good. But that is the basic unit we have to start to try to develop a mathematical model. That's the key. Okay, what is a laminate? If I have 55 such lamina put together, then that becomes a laminate. Okay, now, typically a 24 ounce fabric based laminate build-up requires, roughly speaking, 30 to 40 layers, which would result in a 1/4 inch thick laminate. That's a thumb rule. That's all we can say. The reason I say it's a thumb rule is because to build a 1/4 inch laminate, for example, if I use hand layup, I may only need 20 lamina, wherein I have a much higher resin volume than the fiber volume fraction. On the other hand, if I'm going to use a compression molding type manufacturing operation to make a composite, I may need 55 lamina to build a 1/4 inch thick laminate. Whereas if I use pultrusion, which is in between these two, I may need only 40 layers. So we have what I call a thumb rule type stuff for a 16 ounce per square yard fabric, or for 24 ounce per square yard fabric, or 100 ounce per square yard. How many layers of lamina that are required to make a 1/4 inch or a 1/2 inch or whatever thick laminate for different kinds of manufacturing processes. So there are a lot of caveats I put in there. So please, at least remember, I need a lot of layers of lamina to attain 1/4 inch or a 1/2 inch thick laminate using compression molding, I need fewer layers of lamina if I'm going to do this build up of a 1/4 inch or a 1/2 inch laminate using hand layup. Okay, what does that mean? This implies, my statements imply that fiber volume fraction is much lower in terms of hand layup, right? I just said 55 versus 20. So typically with a hand layup, you will not get much more than 30% if you are lucky. If you are not a very good hands-on person, you don't even get 30% fiber volume fraction. Whereas if I go to compression molding or if I go to pultrusion, I will have much higher fiber volume fraction. Which means what? I'm going to get higher strength, higher stiffness, higher durability. The resins are the Achilles heel, wherein they get affected most first.
Sir, is there any fixed data for the number like 55?
Yes. The answer is yes. Again, when I say a number, like let's take pultrusion. I'll throw a number to you right now since you asked the question. Let's talk about pultrusion. Say I want to build 1/4 inch laminate. Let's say that. If I have a higher density fabric, common sense tells you I need a fewer number of layers of common sense, right?
Yes.
Okay. The whole design is 80% common sense, let me tell you. Anyway, all right. Giving you a number for a 18 ounce per square yard fabric, we need about 32 layers to build a 1/4 inch laminate using pultrusion. That's the answer to your question. In composite, these are design philosophies. In composite, our design philosophy is focused primarily on strain-based approach as opposed to stress-based approach. Remember those words. When you deal with an isotropic material, it doesn't matter because strain versus stress is a constant number, doesn't matter. But it does matter when I'm dealing with anisotropic material. Why? Because I have different moduli in different directions. That's why it matters. Therefore, we much prefer to focus on my limit state is based on certain amount of strain, not based on the strength or the stress. So anyway, all these issues I discussed in my textbook.
On the right bottom, how the resin is getting infused, and this is the resin infusion in progress under vacuum conditions. So you can see about half the width as we infuse, and as you suck the air out, create more vacuum, then you're going to see the resin progressing from left to the right. And under the mechanics of materials approaches, we have extensional modulus in fiber direction, which is along the left to right type thing in this figure, whereas the transverse direction is from bottom to the top. And these two properties, longitudinal versus transverse, are going to be somewhat different depending upon how the fabric is laid out, and it could be vastly different, or it could be nearly identical depending upon the fiber volume fraction in the longitudinal direction versus the transverse direction. I will be showing you some of the equation developments in a minute, but before I go there, I just want to say there are a couple of other theoretical approaches to determine the composite lamina properties. These are known as the theory of elasticity-based approaches, as well as the numerical evaluations based on finite element, finite difference model. We will not be talking about those because that is beyond the scope of this presentation. Now, let me define first what is a fiber volume fraction, what is a resin volume fraction, before we figure out a very, very simple mechanics-based approaches to find the modulus in the strength, in the longitudinal and the transverse direction, as well as the horizontal effect and shear modulus. So in this slide, the fiber and matrix volume fractions are defined as ratios of fiber volume or matrix volume to composite volume. That is why we say lowercase bf divided by lowercase b sub c, which is the composite, that is called fiber volume fraction. Whereas lowercase bn, that's the matrix, divided by b sub c, that's a composite volume, that ratio is called matrix volume. And these are identified in terms of equations 2.11, 2.12 from my textbook. I just want to keep it in line with that. So if you want to learn more about it, you can get into a lot of detail in that textbook. Here, the sum of these two, Bf plus Bn, is the total composite volume, assuming there are no voids, 0% of voids. These fractions are computed, very importantly, to find the stiffness properties, which we will see in the next couple of slides after going through these very basic concepts. Equation 2.2, this slide, the very last equation, illustrates what I said in my previous statement. These fractions can be converted to functions of mass density fractions through basic physics, meaning multiplying it with appropriate specific gravities through basic physics, and I will not delve into that for now. The next slide talks about voids and how are they formed during manufacturing process due to improper cooling or excess moisture, bubbling of a chemical, or even overcrowding of fibers. Similarly, resin-rich areas are possible, which lead to strength degradation. However, we are going to be assuming, as you see in my next slide, these fibers are uniformly distributed, and also the resin is uniformly coated around the fibers. But the important message here is that, as a thumb rule, if you have 1% of voids, that will reduce the strength of the composite by about 7 to 8% in the strength. So that's why you need to minimize the void. In practicality, the void percent should be around 1% or even less. Many factors play a role in void formation, including temperature, Q rate. But now I will not go into too many details in that regard. And the volume fraction equation that I showed there from 2.10.1 to 2.10.6. Finally, the final equation very bottom of that is the volume fraction. There's rho C theoretical is here there minus the rho actual divided by rho C theoretical gives you the volume fraction. The measurements are not easy to establish the volume fraction, but under the scanning electron microscope, we were able to measure the void content with a reasonable degree of accuracy. The next slide is a very quick example. It's a 5 kg of the topic composite with the 60% fiber volume fraction and the specific gravities of both the fiber and the matrix, 2.5 and 1.5. This is a very rudimentary example to illustrate the use of these about equations. These density of specific gravity numbers for glass and resin that I gave you here are average values, and there is a range for these values as I identified in my text. Now we want to find density of the composite and also mass and volume fraction. That's what I'm going to show you in my next slide. So here you can see the density of the fibers, as I showed you the specific gravity of fiber is 2.5, of the matrix is 1.5, the corresponding to multiplied with water density. So in British units, that is 62.4, the SI unit that is 1000 kg per meter cube. Typically, glass composite specific gravity is around 2.1, and in imperial units, its density, the composite density I mean, is around 120 pounds per cubic foot. So that gives you an idea. And this slide deals with the development of mass fraction of fibers and matrix. Mass fractions are about 30% higher than the volume fraction. Please note that. These mass fractions I'm dealing with correspond to essentially based upon the volume fraction equation that I developed in equations 2.11 and 3.12 in the previous slides. And I will not get into the basic computations, but I'm sure you very easily follow where I'm heading from the volume fractions to the mass fractions. On this particular slide, why you guys need to show these above equations? This is to derive the stiffness or modulus properties of the composite as a function of these fractions of fibers and resin. Any theoretical formulation, please note, is based on certain assumptions. Many equations developed. Some of the equations that we developed here are based on the following assumptions. But before I go into these assumptions, this is what is called a very simple rule of mixtures that we deal with composites. And I have already alluded to a couple of these assumptions, but I will read them out loud for you. Here, combination of fibers and matrix of constant thickness throughout the composite lamina. You will see that picture in the next slide. Fiber and matrix are perfect bond with no void. I said that on the previous slide. Elastic response is linear, namely looks like hollow. Fiber and shape distortions during manufacturing, during placement of the fibers, we are assuming there is no effect, even though that's not 100% true. I already told you there will be certain formations of the kinks, and that will affect the local stress concentration effect, also the fatigue effect. The above leads to stiffness properties and Poisson's ratios of the rectangular composite of unit thickness in the longitudinal and transverse directions, including transverse shear modulus. The next slide is essentially an idealized view of fiber and matrix and their corresponding thicknesses as shown in that figure, where that particular element is subjected to longitudinal stress. The next slide, now I'm establishing an appropriate equation for Young's modulus, E-value of a composite by simple force equilibrium equation where longitudinal forces resisted by a composite of that infinitesimal element is equal to the sum of the forces resisted by the fiber and the matrix, which are given in equation 2.13.1, the very top equation. To arriving at the following equation, plus 2.14, is to note that, or recognize that, the strains in the composite, fiber, and the matrix are identical. That is a kind of an assumption, and if you use that assumption, the strains are identical in all three phases, meaning the composite, fiber, and the resin, then you get equation 2.14. Perhaps for those who forgot the definition of Poisson's ratio, I might add that it is the ratio of contraction strain in the direction perpendicular to the stress direction that is shown there in the previous slide, divided by the strain in the loading direction. Again, the derivation details in terms of the Poisson's ratio of a composite is equal to the Poisson's ratio of the fiber, which is approximately 0.2 of that multiplied by the volume fraction, add that to the Poisson's ratio of the matrix. That's why I said mu1 to m stands for matrix, which is in the range of about 0.3. Multiply that with the volume fraction of the matrix. And this slide develops a derivation for transverse elastic modulus. To find the appropriate transverse elastic modulus of the composite, meaning the modulus perpendicular to the longitudinal modulus as we said earlier, transverse stress is applied by idealizing materials as rectangular boxes as we did before. Assuming axial stress in the constituents of the composite are identical and uniform, keyword, these are all assumptions, then the total extension is sum of each constituent part, which is given in equation 218. So this is what is called equation 218. It's based upon the inverse rule of mixture. And in a similar manner, we assume the infinite shear stress on both the fibers and matrix are identical. Shear deformation is sum of deformations of fiber and matrix to arrive at this equation number 2.20. In this example, we are using fiber volume fraction of 60%, as we did in the previous example, to illustrate the point. This implies resin volume fraction is 40%. Repeat, weight fractions are higher than volume fractions due to higher fiber density or higher fiber density than resin density or higher specific value fiber that suit specific gravity population. For those not very familiar with the SI unit, 90 GPa here in this particular example that I'm showing you is equal to 90 GPa is the elastic modulus of the fiber, there are 4 GPa of the metric. So 90 GPa translates to approximately 13 million PSI. That implies about 2.4 times lower modulus for the glass fiber than steel. Please note, this is the S-glass fiber, not the E-glass fiber. Typically, the E-glass fibers have a modulus of about 10.5, 10.6 million PSI. Now, the next slide deals with the elastic modulus computations based on the rules of mixture, but the reverse rules of mixture, as we talked about earlier, as we derived equations 214 and 218 respectively, the composite modulus is about 55.6 GPa. All I have done was plug in the volume fraction of 0.6 for the fiber and the fiber stiffness, which is about 90 GPa. Added that to the volume fraction of the metric, the 0.4 multiply that with the modulus of the metric, which is 4 GPa. So what you're finding is the longitudinal modulus that is about 55.6 GPa compared to 90 GPa for the fiber. This essentially translates to approximately 8 million, roughly speaking, 8 million PSI in the longitudinal direction, which is a unidirectional composite. And the transverse composite is close to not quite 1.4 million PSI. So that essentially gives you a walkthrough of how to find the stiffness of a unidirectional composite. Now, I would like to now move to a much more complex topic. Let me first say what the topic is, then I'll tell you about the complexity, where this topic can be used and all that first, then I'll talk about the complexity. Now we're going to get into a more difficult concept of a lamina and a laminate. A very thin layer of the composite is commonly referred to as a lamina. And multiple layers stacked over each other is called or referred to as a lamina. How here we refer to a laminate whose thickness is very, very small. Means what? It means less than 10, the thickness should be less than 10% of the smallest dimensions of a laminate in plane. And I want to show you how to establish relationship between the stress and strain of a laminate for a plane stress condition, which we call, implying that any stress variation in the thickness direction is neglected. That is called a plane stress condition. This essentially is made to reduce the complexities associated with the derivations and simplify the equations without having much loss of accuracy. Now, so you can see the various laminates, and some of these laminates may be having unidirectional fibers in the X direction, other laminates may be having unidirectional fibers in the Y direction. There are no fiber, the one in this case, in this particular case, in the Z direction. But you could also have in one of these layers of lamina a 45 degree, plus minus 45 degree based fiber fabric orientation. The reason we need to have these different kinds of orientations is because in some elements of a member, we want to have high tensile strength in the longitudinal direction. In other elements of the member, we want to have fairly high shear strength in the web, that is, that element in the web, where we need fairly high shear strength and we need high longitudinal tensile or compressive strength in the top line and the bottom line of a structural cross-sectional member. And that is why we need to not only have different orientations, but at the same time, we need to figure out how we are going to analyze all these under a base coordinate system. So, the stress and the strain relationship under a linear plastic state of stress on the form of an infinitesimal element in a Cartesian coordinate system are shown there. As you can see, here, what I want to emphasize is this slide introduces the state of stress in the three-dimensional view, and positive direction is shown with the arrow pointing away from the base of that view. So that is the important message. So from these two very important slides, no doubt, I'm the first one to admit it's very somewhat difficult for people to comprehend it the first time. But with these slides, two slides that I just showed, I'm going to now talk about how the isotropic material is different from the anisotropic material. So I'm going to start from the bottom up. Isotropic material properties are like steel and aluminum, and these properties are independent of the loading or the direction of the material axis. Whereas, when I go one step further to item number 3, this is called transversely isotropic. In this, we're talking about having one symmetric plane that is isotropic, as I've shown you on the figure on my right side. So this is called, like, typically people consider timber as a transversely isotropic material. Then I complicate it further, then that's known as the orthotropic material. Fibers are oriented between mutually perpendicular symmetric planes, simplified version of this even more complex material system known as totally anisotropic system. I admit this is a difficult concept, no doubt, but please bear with me. So what I'm trying to do here is, in terms of this plane stress problem,
You can stop here.
I am trying to
Okay. I can assure you there will be no more mathematics beyond that level. Let me start with that. And even this much I showed only to tell you how things can get complicated from one stage to the other. Thirdly, what has this anything to do with concrete? What has this anything to do with FRP rebar? That's the next question, right? Okay. So, in terms of chapter 2, all we have done was, if you want to learn anything about composite, anything rudimentary of composite, all you need to know is the rule of mixtures and the inverse rule of mixtures. What has that anything to do with FRP rebar that I showed you? the important thing there is you use those very, very simple equations. I'm talking about chapter 2. I'm not talking about the third chapter, and the fourth, fifth chapters get even more difficult, so we're not talking about that. When you deal with an FRP rebar, what we are talking about is the use of rule of mixture and the inverse rule of mixture to find the stiffnesses or the moduli in the longitudinal direction and in the transverse or radial direction. That's all. You must know that. There's no way out of that if you want to be a designer of a concrete beam with FRP reinforcement. That's what we are talking about. And now you can see that if you go to 60% fiber volume fraction, 70% fiber volume fraction, you will get a fairly high moduli in the longitudinal direction of the order of 6 to 7 million psi or something like 60 MPa, GPa. I keep mixing myself up, 60 GPa. That's what you're going to get. But in the transverse direction, you have a very low stiffness. Why? There is no fiber in the transverse direction. As far as the rebar is concerned, it's all in the longitudinal direction. So the stiffness in the transverse or the radial direction is essentially a function of resin stiffness. That has some advantages, some disadvantages as usual, but the major disadvantage is that under thermal expansion, that in the radial direction is going to be large. You understand what I just said? Now, that can be contained in a different manner. I won't go there, but that's the issue I want you to kind of appreciate. So with that, we will have a wonderful tea break. Thank you.
One question. Actually, you were told that the voids affects the strength very badly, up to 8% to 77%.
Right.
So, how can we minimize the voids? Any particular mixing method?
If you recall, I identified there are 3 or 4 reasons why voids are coming. The best way, you can never avoid it, but the best way to minimize it is by having proper cure rate, by having slower speed of production, by having proper combination of fiber resin volume ratio. So these are the ones. And then in terms of the resins, we don't want the resin to bubble up, and it does. But that is where we want to control it. The exotherm needs to be controlled. See, we were discussing last night, somebody came talking to me. Sometimes what we do to minimize voids is you cure the same sample at 3 different time space. In other words, you don't want to bump up to say 300 degrees. If you don't bump up, you don't get a full cure, right? Sure. Therefore, we take it up to say 200. These are just numbers to illustrate, so please don't take it. So you cure it partially is the word at 220 degrees, say, for 1 minute. Then let it come down a bit, then cure it again. But all this takes time and money, you see. Okay, somebody also was asking me yesterday about how to make stirrups. I told them it can still be a continuous process and make stirrups. A discontinuous process is to make stirrups is to utilize thermoplastics and heat it. That's a discontinuous process. But the continuous process to make stirrups is, I shouldn't say continuous, semi-continuous, is you partially cure a composite, bend it, and then let it cure even in an oven or by nature. So that is the response. I forgot who was asking me the question. I did not mention that the partial cure, but we can do the partial. Have you done a partial cure? Okay, you can do the partial cure, bend it to whatever the shape you want, and then let it cure under environment, or put it in an oven. If you're going to put it in an oven, it's going to consume energy, it's going to cost money, it's going to cost time. But yeah, any which way, so that's another way to. Did I answer your question? Yeah, that's the only way you can do it. The process, you have to take your time. This is like cooking. You go to your mothers and ask, a good cook is always going to take time to come out the recipe right? Exactly the same thing. Void reduction is identical to that.
Yesterday you mentioned the cure time. I mean, if we are doing it by nature, the ideal time is 28 days. So it's the same for this.
No, absolutely not. The cure time can be 1 minute, depending on the peroxide that I'm going to put in there, or it can be 100 days. You see, so we can adjust that's the message. We can adjust the cure time. We can put the retardants in the resin and reduce, increase the cure time. You see what I mean? It'll cure. Make sure it must cure 99.56%. Otherwise, your durability will be suffering. Anytime you have an open molecule in your resin that is uncured, obviously, then that is where the composite initiates degradation. So again, you cannot be a polymer chemist, but at least if you understand it, there are differential scanning calorimetry. Have you used it? DSC. That will tell you right off the bat in almost less than 5 minutes or 3 minutes how much was the cure percent. You understand? Have you used DMTA, the dynamic mechanical thermal analyzer? That will also tell you where the curing problems are, if any. So again, the DMTA dynamic mechanical thermal analyzer is a torsional system. Why do they do that? It's easy to figure out from the shear response point of view what the stiffness is compared to the tension compression response point of view, because that is driven by the shear strength, which is the least value in terms of the resin, unlike the fiber. So we'll take a bit. Yeah.
So whether this fiber orientation has any effect on strength?
Of course. That was my chapter number 3. I didn't want to go there. I'll lose all of you. You may not come back after the break. So I stopped it right there. Extremely important. That is where all the composites, this is not an easy topic. Up to 2nd chapter, it's easy, relatively. But once you go into 3, 4, 5 chapters, that is what we are talking about here, if you look at why do we have fibers in the x1 direction, in the oriented in the x2 direction, whatever the directions are. Why do we have a 45-degree fibers? All this discussion is to make you appreciate that the strength of the material is dependent upon the orientation and also the fiber volume fraction in that direction. In reality, in real structures, you will not have all fibers oriented in one direction. It's not the case in real structure. Therefore, we need to have a balance between 0 degrees, 90 degrees, plus minus 45 or 60, 90. All these permutations and combinations come into picture depending on the functionality of the structure, depending on how you want to design. If the shear dominant structure, I will have plus minus 45 lot more than axial force dominated structure. And the rebar, why did we not have any kind of fiber along the circumferential or along the radial direction for a rebar? Obviously, it is primarily an axial element, number one. And number two, it is confined in concrete. Therefore, the radial directional properties are not as important. Thank you. Any other questions?
Coefficient of thermal expansion is different in longitudinal and radial direction.
Absolutely. I already told you the coefficient of thermal expansion for 60 to 70% fiber volume fraction in the longitudinal direction is approximately 2 to 3 microstrains per degree F. Whereas in the radial direction, it is about 25 to 30, it's about 15 times higher in the radial direction. So, luckily, the rebar is confined, that's the word, confined in concrete. So, it does not let it expand. The concrete does not let the rebar expand under different temperature conditions. Now, good question. It will lead us to the concrete design. If your cover is very small, the cover will split. Therefore, you need an adequate cover. You follow me? You need an adequate minimum cover for other reasons too, but also to make sure my cover is not going to have a split tension problem.
Does providing helical ribs or anything help in containing that expansion?
Yes, it does, but nominal. We have to be careful. Am I talking as a theoretician or am I talking as a designer? Now, we will talk as designers, not as theoreticians. Every analysis has assumptions, you see. So as long as you fit yourself into these assumptions, the theories are good. Let me tell you this much. In terms of design of a composite system, theories are wonderful, wonderful. We need some way to do this, but we never implement a structure with composites without fully testing it. It's not like isotropic material. Believe it or not, the Boeing 787 work was going on for 25 years. I was not involved in it. I wish I were. Two of my students are involved in it, I can tell you. But they asked me to do some work. I couldn't do it for whatever reason. Never mind. But my message there is, that's a composite, right? And they did 25 years of testing and even though they have a ANSYS-based FE modeling, blah, blah, blah. Yeah, you have a question.
Sir, in IRC 137/2022, it has provided that GRP temperature as low as minus 120 degrees Celsius in practical sites.
Is that,
But why it is recommended in
you said 1 minus 20.
minus 120 degrees Celsius?
Yeah, that is the key. And what happens is, even we in the US code do a similar thing. What did I tell you? TG is a reference line. How much is the TG in terms of F? 210 or 200 something. Look, for a resin, TGs are slightly lower than for a composite. The TG goes up because, not because of the resin, but because of the fiber. Anyway, it's in that range. Now, what happens is the resin begins to soften, even at about 20-30 degrees below TG. That is why they recommended that number. I think I showed yesterday some range. Some people say even at about 120 degree F, that is like what? Almost 90 degrees below the TG. But we take a slightly liberal attitude and we say about 30 degrees below TG. That it you start. Did you read the reduction factors due to temperature? I flashed it today. That is why. Okay. All right. Anything else?
Sir, but
Oh.
but this can be done in minus 40 to 50 degrees Celsius also. Then why we only take or mention at is minus 120 degrees Celsius? That is too much of.
That is too much. That's what I said. We don't use that minus 120 at all.
Yes.
We don't. If somebody tells you it's minus 120, that is dead wrong. But I don't want to get into your code. When I'm going to argue with mine, I would say that I have no problem. You see, we will talk about, we are here to really talk about FRP design of rebar for concrete. Let me tell you something. I was the one who introduced the compression failure concept for concrete beam column design. You don't believe the kind of resistance I got for introducing. FRP cannot be done, designed as a tension failure unless you have a huge. So they almost told me I know nothing about concrete. You know, I said I graduated from a guy who was the president of the society. So, but you get into these problems. You know, you have to face it up. Galileo, what did he say? Earth was circling around. He was about to be butchered, right? Vinyl ester. For polyester, that factor is somewhat lower. And you can see, I don't want to, without knowing the details, I didn't want to contradict the gentleman here, but talking about minus 120 is absolutely ridiculous. That doesn't make any sense. I think really, to be fair to the people who have put the document together, I would simply say that may have been an editorial error. That's what I told him. But as you can see, from the temperature point of view, even we also say that the reduction would start after 90 degrees, you see? Yeah, so that makes, we have done the testing and evaluation. I'm going to give this book, this has lots of examples, but this is not a code, but there are many, many errors in it. Very unfortunate, but that's what happens in this day and age. People are in a hurry to do things, and that creeps errors into it, right? So I hope that doesn't happen with your design part of it. That will be most dangerous. Anyway, so we concluded that, and now we will go back to our yesterday's presentation, focusing on FRP rebars. I gave you a flavor of how to do the computation for a most, perhaps the simplest element of GFRP, you know. If I go beyond that, I know for sure I'm going to lose you. Therefore, I'm going to leave it there and go back focusing on why we are here, that is the design of concrete. So, if you please go back to yesterday's thing. What time we had to break again? 1 o'clock? Not much time. All right. Or 1:15.
So yesterday, first presentation.
Not that one. I mean, the one, my 300 slide one. Yeah. Please go to slide number 65. Next one, 66. I think we talked enough, don't you think, about different manufacturing settings in a broader sense. I don't imply, when I say we talked, I don't imply at all in any in-depth sense, please. We talked in a much broader sense. I'll be happy to come back, discuss at any great depth you want, but let's wrap this up, then in terms of the concrete, then we can go if time permits.